A trace table is a way of following an algorithm by hand, recording the value of every variable after each step. And the reason it exists is worth stating before the method, because it explains why exam questions keep asking for it. A program can run without crashing and still be wrong. It produces an answer, just not the right one. That is a logic error, and no error message will tell you about it. The only way to find one is to follow the algorithm as the computer would step by step and watch where the values stop matching what you expected. A trace table is that process written down. It is also, incidentally, how you answer the question, what does this algorithm output, when the algorithm is too fiddly to read at a glance, which is most of them. Setting one up has 3 steps. 1. One column for every variable in the algorithm. 2. An extra column for output, because what is printed is not a variable and needs recording separately. This is the column people forget. 3. Work through the algorithm one line at a time and add a new row whenever a value changes. Now the rule that catches people out. You record what actually happens, not what you think the algorithm was meant to do. That sounds obvious, and it is the hardest part in practice, because when you have written an algorithm yourself, you tend to trace your intention rather than your code, and that is precisely how the bug survives. Trace what is written. Let us trace one properly. The algorithm is on screen. Line 1 sets total to 0. Line 2 sets count to 0. Line 3 starts a loop that repeats 3 times. Line 4 reads a number into num. Line 5 adds num to total. Line 6 adds 1 to count. Line 7 is the end of the loop, and line 8 outputs the total and the count. Test data 10, 5, 20. Line 1, total becomes 0. Line 2, count becomes 0. First time round the loop, line 4 reads 10 into num. Line 5, total becomes 0 plus 10, which is 10. Line 6, count becomes 1. Back to line 3 for the second pass. Line 4 reads 5. Line 5, total becomes 10 plus 5, 15. Line 6, count becomes 2. Third pass, line 4 reads 20. Line 5, total becomes 15 plus 20, 35. Line 6, count becomes 3. The loop has now run 3 times, so it ends, and line 8 outputs 35 and 3. Notice 2 things about what just happened. Every time a value changed, a row appeared, and the row records the line that changed it. And the output column stayed empty until the very last line, because nothing was printed until then. Both of those are exactly what an examiner is looking for. Now the thing trace tables are actually for. Suppose the same algorithm had a bug. Line 6 read count assigned 1 rather than count assigned count plus 1. Assignment instead of addition. Run it and nothing crashes. The program is perfectly valid. It outputs 35 and 1. Now 35 is right, so a quick glance at the output might not even alert you. Trace it and the fault is unmissable. First pass, count becomes 1, which looks correct. Second pass, count becomes 1 again. And there it is, a value that should have changed and did not on a specific line. You do not merely know the program is wrong, you know it is wrong on line 6, and you can see why. That is the difference between the answer and the method, and it is why a question showing you a faulty algorithm and asking you to identify the error expects a trace. Guessing might find it. Tracing always does. The rules to follow, and each one corresponds to a way marks are lost. 1 column per variable, plus a column for output, and output is not a variable, so keep it separate. Add a new row when a value changes. Do not overwrite a value in place, because the history is the point. Trace what the code says, not what you intended it to say. Work strictly line by line in the order the algorithm actually executes, which means following the loops and branches rather than reading down the page. And put the test data in before you start, so you are not inventing inputs as you go. On loops specifically, go round exactly as many times as the condition says. Off by 1 errors, running a loop 3 times when it should run 4, are among the commonest mistakes in this topic, and they happen when someone traces the first pass carefully and then assumes the rest. 2 more uses worth knowing. First, working out what an unfamiliar algorithm does. A question might give you an algorithm with no explanation and ask what its purpose is. Tracing it with a couple of values usually makes the purpose obvious. You watch it accumulate a total, or find the largest value, or count how many items meet a condition, and the answer names itself. That is often easier than reading the code and reasoning about it in your head. Second, checking your own answer. If a question asks you to write an algorithm, tracing it with sensible test data before you move on catches errors while you can still fix them and takes about 90 seconds. Given that logic errors produce no warning at all, 90 seconds is an extremely good trade. 4 things to take into the exam. First, always include an output column and only fill it when something is actually printed. Its emptiness through the middle of a trace is correct, not an omission. Second, 1 row per change, keeping every previous value visible. The sequence of values is what shows you're working, and working is what a trace table question awards. Third, follow the algorithm exactly as written, including going round loops the precise number of times, rather than assuming what happens after the first pass. And fourth, when a question asks you to identify an error, say which line and why. A trace lets you name both, and naming both is worth more than saying the count is wrong.